Good morning, and welcome to my talk on the benchmark for data sortedness. My name is Aneesh, and this is a work in collaboration with my colleagues Kostas, Subhadeep, Matt, and my advisor Mano Satanasolis. By the end of this talk, you will learn how data sortedness is a valuable resource that indexes can take advantage of to improve their overall performance. Indexes in databases organize data in a convenient manner so as to facilitate efficient queries. This, however, comes at a cost. To store the index, we pay the cost of space amplification, whereas to build and maintain the index, we pay the cost of write amplification. So what essentially is indexing? You can think about indexing as the process of inducing or adding structure to an otherwise unstructured data collection. Popular indexes in databases include B trees, hash maps, or more recent designs like the LSM trees or even skip lists. So during index construction, if we already have sorted data, then we can do something fast rather than regular insertion. For example, bulk loading in a B tree. For not sorted data, say for example, scrambled data, we have the standard ingestion technique like inserting from the root node of a B tree. But what if the data has some degree of sortedness but is not completely sorted? These are very common cases. Take, for example, the TPCH line item table. If data arrives sorted with respect to the ship date column, then we see that the data in the two other columns, receipt date and commit date, arrive almost sorted or nearly sorted. Such a case would be true for all cases wherever we have correlated columns. Other examples of intermediately sorted data include time series data or even stock market data. So going back to our problem, we know what to do for the two extremes of data sortedness. That is, we have standard ingestion technique for not sorted data, and we have faster ingestion techniques like bulk loading for fully sorted data. Note, bulk loading requires the entire data to be available beforehand, prior to data loading, so that we can build the index bottom up. Now we want to ask, what if the data is intermediately sorted like shown in the slides? It turns out that intermediately sorted data is treated in the same class as scrambled data in present literature, which means for even if the data is nearly sorted, we are left with no other technique rather than standard ingestion as of now. To offer better context, let us visualize this further. If we plot the increasing data sortedness on the x-axis and compare the ingestion latency, we have the extremely fast ingestion techniques like bulk loading. Then we have standard ingestion, which as of now doesn't look to be accounting for data sortedness. But what we want is something along the blue line. That is, we pay less cost as the data becomes more sorted. Why? Because if there is already inherent structure in the data, we want to take advantage of it and do less work. So is this even possible? We would like to point out that so far, the performance of indexes with varying data sortedness has been practically unexplored. Because of this, there is also a lack of a proper testing framework to evaluate indexes with varying data sortedness. Thus, we propose BoDS or benchmark on data sortedness. It carries a synthetic data generator that can create differently sorted data collections and a benchmarking suite that encompasses this data generator to provide an end-to-end tool for evaluation of indexes with varying data sortedness. So through the rest of my talk, I would first walk you through how we can quantify data sortedness with a few popular metrics. Then we will look at how we generate data in the synthetic data generator at a very high level. We will then look into details of the benchmark before seeing the benchmark in action. So how do we quantify data sortedness? Various metrics have been proposed in the past that quantify data sortedness. For example, we have inversions that count the number of pairs in incorrect order, runs that count the number of increasing contiguous subsequences, and exchanges that count the least number of swaps required to establish total order in the data collection. While being fairly intuitive, these, however, have a few drawbacks. Take, for example, if we have the following data collection. Here we have two increasing subsequences, but the subsequences themselves are unordered. This is a phenomenon called global disordering, and it turns out that inversions cannot handle such a scenario very well. If we have another example where every entry is swapped with its immediate neighbor, this is called as a local disordering. It turns out that while inversions can handle local disordering really well, runs cannot do so. So while exploring different metrics to quantify sortedness as part of the benchmark, we came across this interesting metric proposed in an ICTT 2011 paper. This quantifies data sortedness based on two parameters: by how many entries are out of order and by how much. The number of unordered entries is denoted by K, whereas the maximum displacement among the unordered entries is denoted by L. So the combination of KL not only overcomes the global and local disorder phenomena that we spoke about a little earlier, it essentially quantifies the effort required to establish total order in the data collection. Is a mere combination of KL enough to capture all facets of data sortedness? Say we have the following data collection visualized by position and value. The gray band denotes the L window within which entries can be displaced. What if we want to distribute the unordered entries slightly differently, like shown on the right? To enable such scenarios, we add another dimension to the KL sortedness metric, one for displacement distribution. Here we use a generalized beta distribution bounded by the L window within which the entries can be displaced. Using a beta distribution has various advantages, as it allows us to simply mirror various other distributions by simply changing the alpha and beta values. Say if we set alpha and beta equal to 1, we can get a uniform distribution, or we can also get distributions with peaks, valleys, or even those that are skewed with a tail. So how do we generate data in our synthetic data generator? At a high level, we follow a two-step process. First, we generate a fully sorted data collection based on the number of entries required. Then we induce unsortedness to this data collection by the given K and L. How do we do this? We simply use an idea of swapping entries separated by at most L places, and the destination of the swap is picked using a beta distribution. This kind of reverse engineers the entire process of generating differently sorted data collections. Moving over to the benchmark, we support two kinds of workloads: insert-only workloads or mixed workloads with interleaved reads and writes. For insert-only workloads, we have two types. Workload A uses bulk loading to load 100% of the data, while workload B uses individual inserts or standard index ingestion for loading in the entire data collection. Workload C is a mixed workload with interleaved reads and writes that contains no preloading phase, whereas workload D contains a preloading phase where we warm up the database with 80% of the data using bulk loading. We conduct the mixed reads and write operations at a 50-50 ratio on the remaining 20% of the data. Workload E is very similar to workload D, except that we use individual inserts for the preloading phase. As inputs to the benchmark, we take in the number of entries required, what would be the payload size, the number of unordered entries or K, the maximum displacement or the L, and the parameters of alpha and beta for the generalized beta distribution. The benchmark itself has a very simple architecture. We have a coordinator that communicates between different components of the benchmark. It first calls the data generator to create a data collection. The data collection is then parsed through a workload generator that creates the different workload files based on the workloads that we just discussed. Every workload file is then fed into a workload executor that executes them on a database of the user's choice and measures the execution time. As part of the benchmarking action, we focus on two metrics: the ingestion latency in case of insert-only workloads and the overall operational latency for the mixed workloads. With the data setup, we use 16 million key value pairs, which approximate around 4 gigabytes of data when we use an entry size of 256 bytes. We execute all our experiments on an Amazon EC2 instance with 4 gigabytes of RAM and 40 gigabytes of solid-state root storage. The experiments that I would primarily talk about in this presentation include those in Postgres, which is a state-of-the-art row store system. Postgres allows us to use unlocked tables that can isolate the index performance without any other overheads, for example, like those introduced by the write-ahead logging. We use a B tree on the key or the ID column of the table. First, let us look at the raw ingestion performance. Here, we plot the insert latency on the y-axis, and on the x-axis, we try out different KL sortedness combinations as percentage of the total data size. To simplify, the first half of the x-axis shows increasing K, whereas the next half of the x-axis shows increasing L. We also have the two extremes of data sortedness on the x-axis, which is fully sorted as well as the scrambled 100-100 dataset. As expected, bulk loading, denoted by the black line, is extremely fast. Though not visible due to the scale of the axis, there is actually a performance difference of around 19% between the fully sorted workload performance as well as the scrambled performance. This is mostly due to the sorting overhead. While we expect systems to kind of handle data sortedness to at least some extent, it turns out that there is no difference when ingesting fully sorted data or even scrambled data. Postgres shows no significant difference when ingesting different data sortedness combinations, which means we almost get the same performance while ingesting near sorted data or even fully sorted data as we ingest scrambled data. Moving over to the mixed workload performance, here again, we plot the latency per operation of the mixed read-write phase on the y-axis, while the x-axis has a reduced subset of KL sortedness combinations to just simplify the process. The performance of workload C is denoted by the black line, whereas that of workload D is shown by the blue line, and that of workload E by the red line. Again, for all the three workloads, when we compare their performance for the different sortedness combinations, we see no significant difference. So here we can conclude that Postgres using a B-tree index does not offer any kind of advantage when ingesting differently sorted data. Column store systems, on the other hand, use other techniques like vectorization, vertical partitioning, or even compression to optimize for read performance rather than relying on secondary indexes. Further, we cannot enforce a strict column ordering while data loading, as we can do so in a typical row store using a B-tree index. Thus, we believe that column store systems require fundamental design changes to handle or exploit data sortedness during data loading. However, we did experiment with a few column store systems. MonetDB, for example, offers two kinds of indexes, ordered and imprints indexes. Both are invalidated upon having any updates to the system. So when we did try running experiments with workload A and B, that is the bulk loading and the insert-only workloads, we virtually saw no difference in performance as we varied the data sortedness, because the only cost we were paying is that for vertically partitioning the data and inserting the data into a table. Vertica is a commercial column store that uses projections, which are very similar to ordered indexes, to optimize for read performance. When Vertica receives updates, the projections go out of date because there is no in-order insertion. Again, here, we don't expect to see any significant difference while we vary data sortedness on the performance of the system. Action Vector is another column store system. However, it does support live updates to a sorted column by using a technique called PDT, or positional delta trees. PDT is essentially an in-memory variant of a B tree containing positional information. But based on our experiments with B tree, we again don't expect any significant performance difference as we vary data sortedness. We are still exploring the efficacy of both vertica and action vector systems when we vary data sortedness using our benchmark. So now that we've established that traditional indexes do not exploit data sortedness to improve overall performance, I would like to spend the last part of my presentation to discuss what we can expect from sortedness-aware indexes. A good point to start off would be the read-write trade-off. Every data organizational technique exhibits a fundamental trade-off between its read and write costs. If reads are infrequent and scanning is acceptable, then we can simply append data without taking any additional effort and scan whenever required. However, if reads are frequent and we need good read performance, we essentially pay the cost of in-order insertion to achieve a logarithmic search time or faster performance. This generally can be viewed as standard index ingestion and querying from an index. Thus, every data reorganizational technique, including indexes, exhibits or navigates this read-write trade-off to optimize for either the read or the write costs. What we want now is to reduce the write cost if data is pre-ordered, even if it is only to some extent, which means we're essentially proposing a third axis to this read-write trade-off, one for data sortedness. This way, we're creating a new domain for index data structures that can improve index construction and maintenance by using data sortedness as a resource, while also offering significantly better read performance. This means sortedness-aware index data structures should navigate the read-write trade-off along the sortedness axis to push the red line further down along the dotted black lines. What we want is essentially to increase the indexing efficacy while significantly lowering the indexing cost. So since we spoke about B-trees in this presentation, I would also like to present very briefly our first take on augmenting the B-tree to be sortedness aware. We propose a few design elements, first and foremost of which is the rightmost leaf appends. This is a fairly intuitive technique where instead of traversing every entry through the root node of a B-tree, if the entry arrives in order, we can directly add it to the tail leaf node of the B-tree and avoid the tree traversal cost. Now, if we have a bunch of entries, we can essentially batch them up to create a new leaf and then append it to the tail leaf of the B-tree, thereby amortizing the cost across a bunch of entries. Varying the split factor is another important decision that we take. Every B-tree node splits exactly in half when full, which means almost 50% of the space is going to go to waste if the data is arriving fully sorted or even nearly sorted. So we can adjust the bias in splitting to say somewhat an 80-20 ratio so that we leave more space on the newly created node, which would reduce the number of splits that we perform and improve the ingestion time. We will also tightly pack the leaf nodes or even the internal nodes, thereby improving space efficiency. These two techniques work well directly with fully sorted data. However, to make it work with any degree of data sortedness, we combine it with an intelligent buffering scheme that not only quantifies data sortedness within the buffered entries, it also identifies overlapping entries between the buffer and the tree so as to opportunistically bulk load whenever possible. So when we look at the performance, we have the individual inserts as before. We have the fast bulk loading performance with a black line, and the blue line is exactly what we expect. We are paying less cost or less indexing cost as the data sortedness increases. A point to be noted is that we are using here a very small buffer compared to the total data size. And even with that small buffer, we are able to achieve close to bulk loading performance even for nearly sorted data. So to conclude, we would like to reiterate that the performance of indexes with varying data sortedness has yet to be explored, and BoDS lays the groundwork for sortedness-aware testing. Through our experiments, we found out that classical indexes do not exploit data sortedness to any extent and to improve index performance. So we envision not only to navigate the read-write trade-off using the sortedness axis for index data structures, but we also want to continue sortedness-aware explorations for other index data structures like LSM trees or even other sortedness aware algorithms like join algorithms. Thank you.